Hello, everyone. Welcome. Thank you for joining today's webinar. I'm just going to take a few more moments to let the last few people come in before we get started. And after that, we'll get this show on the road. And okay. Hello, everyone. Thank you for joining us today for our webinar, Don't Wrestle with Your Data, the What, Why, and How of Data Wrangling. My name is Samir Warudkar. I'm the product engineering head here at Express Analytics, and joining me is data engineer Prateek Bhurkay. In today's presentation, we will be covering the topics of data modeling and data testing. Today's presentation is the third in a webinar series. Next slide. So on the 6th of May, we had covered the first two topics of the data wrangling process, which is sampling and exploring your data. On the 11th, we covered cleansing and organizing your data. And finally, today, we will be covering modeling and testing your data. So real quick before we get started, a review of kind of just information about who we are here at Express Analytics. Express Analytics is a business intelligence company that's been in the industry for about 20 years. We were founded by a number of Big Five managers back in 1999, and we've offered a number of solutions over the last 20 years to such clients as Walmart, Sony, and Solar Turbines, which is a subsidiary of Caterpillar. We've completed projects in Tableau, SAS, Informatica, and AWS. And we are currently in the process of developing a customer data platform called Oyster, which we plan to bring to market very soon. A couple things of housekeeping before we get into our content for today. Number one, we will be having a series of survey questions for you guys to answer. We will just kind of bring those up as they are relevant and let you guys go ahead and answer those. Also, attendees will be in listen-only mode during this webinar, but please do not hesitate to key in your answers into the chat, and if we have time at the end of today's presentation, we will answer those. Otherwise, we will have someone from our team reach out with the answer at a later time. Other than that, today's agenda will start with a quick recap of the previous webinars that we've had in this series, and then we'll move on to step 5, which will cover data modeling, and that will be covered by Prateek, and then model testing, which will be covered by me. So in terms of the previous webinars we've had, we covered the 4 topics of data sampling, data exploration, data cleansing, and data organization. We discussed how data sampling is essential for choosing the observations that we want to use for our modeling process. And we also discussed not only the modeling, the sampling methods that we want to use, as well as the major errors that we would want to steer clear from, or how to counteract these errors from coming into our sampling process. We also discussed the data exploration phase, which is a key preliminary examination of our data so that we can better understand the kind of scope of what data we should expect to see, as well as what types of errors might come up or might be present in the data itself for cleansing. Data cleansing, therefore, being the next step, is the removal of the flaws in our data that we identified during the data exploration phase. We also called into consideration the organization strategy that our company might have about how the data is stored once it's been cleansed, so that we can have a repeatable method of calling data for evaluation and modeling, as well as making sure that there's a standard format for data for communicating insights across multiple teams. Beyond that, we have our first survey question, which is essentially just a simple question of whether you attended our previous webinar. So we will be giving you a few moments to kind of look that over, and once we have that answered, we will go ahead and get that completed. All right, thank you so much, and we will be ready to move on to our next webinar topic, which is, of course, data modeling. So I'm going to hand things off to Prateek so that he can present data modeling.
So hello everyone, I am Prateek Bhurkay. I am a data engineer with Express Analytics with a background in personal management, training, and even teaching. So I handle the training programs at Express Analytics. And so I'm here today to finally talk about data modeling. So in the previous webinars, we have talked about all the four steps of data, the first four steps of data wrangling. We finally come to data modeling, which is the crux of the data analytics process, because this is the step that actually produces the useful insights for which we put in so much of effort in collecting and cleaning and organizing data. This is finally where the whole process pays off and gives us the useful gold mine of information. Okay, so let us look at what exactly is data modeling. Data modeling is nothing but breaking down behaviors and processes and scenarios into mathematical equations. Why do we do that? Because if we have a mathematical equation, we can then solve these equations to find a solution to these equations. Or we can use these equations to predict the behavior of a system when we know what the situation is going to be like, or what the input variables for the system are going to be like. So data modeling is very crucial is for a lot of different scenarios that you're going to see in an upcoming slide. And basically, we use machine learning to use various algorithms to set the parameters of the model that best fit our data. All right, as you can see right there, our algorithm has fit the data onto what the observations were, and now we have the parameters for our model which we are now going to use. Okay, but why is data modeling so useful? Well, quite a few reasons. First of all, it studies systems and it tells us about the underlying principles which are at work. All right. So let's take an example here of an ice cream shop on a cold winter day. On a cold day, generally a cold day, we have only one customer waiting in line. And our machine learning algorithm notices this. Now, on another day, on a much warmer day, we have 7 customers lined up outside our ice cream shop. So our machine learning algorithm has taken these bits of information into account and has come up with a hypothesis that the higher the temperature, the more number of people you have waiting outside your shop, the more number of customers you have. Now, using this relation, we can use it to make predictions about a situation where we do not already know the outcome, right? So here our data scientist is going to ask a question, what about if we had a cloudy day? To which the machine learning algorithm, using the logic from earlier, says that on a cloudy day, we can expect about 3 people to show up. Now, depending on how accurate our model is, it can be anywhere from 2, 3, 4, or maybe even 5, or I don't know, 1 person showing up, depending on how accurately our machine learning algorithm has modeled the situation. But on this particular cloudy day, we have exactly 3 people lined up outside our ice cream shop, exactly as the algorithm predicted. So why was this important? What's happened here is that using machine learning, we are able to predict approximately how many sales we are going to have, and accordingly, we can keep inventory stocked up. The last thing you would want is on a particularly hot day when you know you're going to have a lot of sales, is that you run out of stock and you've missed out on a lot of opportunity to make quite a bit of profit. Similarly, on a cold day, you might just be wasting space and have stock get expiring in your inventory or your go down, because you have got much more inventory than you can actually manage to move. So finally, this is one method in which data modeling is very useful. And of course, this has so many applications throughout business and also other fields of study that Yeah, we cannot even begin to enumerate all the examples right here. So basically, data modeling helps us to prepare and optimally respond to unknown situations. In this case, the unknown situation was, what if it was a cloudy day? All right. Okay. Now let us look at what are the different kinds of models actually available to us. So there are three main kinds of models. The first is the regressor, which attempts to find a curve of best fit to our data. So using a regressor, once the data is regressed all the variables, we can find out what output do we get for a particular value of the input. So if we have this input, we can use this line and find out, okay, and we will have this output for this input. Okay, then we have clustering, which basically attempts to group points based on their similarities and dissimilarities. For example, these points are similar enough to be part of one group, but are dissimilar enough from the yellow and the green points that they are not part of one of those two clusters. Okay, this is a form of unsupervised machine learning where we, as a data scientist or the user, have very little control over what the algorithm is doing. And finally, it just gives us the output that, okay, this belongs to this cluster, this belongs to this cluster, this belongs to this cluster. Finally, we have classifiers, which will study the properties of our objects, learn from them, and then try to classify objects for which we do not know its properties, whether it is red or blue. And this is how a classifier works. So we're going to look at different kinds of classifiers, regressors, as well as clustering in the upcoming slides. Let us start with the regressors. Now, generally, there are many different kinds of regression which are available to us. The first being, if you notice that your data has a linear relationship, you might have a linear regression might be what you are looking for. If you find that your data follows a slight curve, you have a polynomial relationship on your hands. If you find that, in fact, your data increases uncontrollably, you have an exponential relationship at play over here. If your data starts to taper off, perhaps there's a logarithmic relation and the underlying principle. If you have a classification of either just zeros and ones, then a logistic regression is what you need to use, because the logistic regression will either give you 0, 1, or a probability somewhere in between. And finally, you have the lowest regression, which attempts to fit a more complicated curve to your data points, and if it doesn't follow any of these previous algorithms or previous relations. These are the different kinds of regression. And once our regression is fitted, we can use the regression to predict the output for a given set of inputs. All right. Okay. Now we come to the different kinds of classifiers. We talked about logistic regression already, but a logistic regression can also be a classifier because it classifies it as, is it this or is it not this, right? So 0 or 1. And it uses this complicated function called the odds function to classify whether or not um, an object is going to return a value of true or false. For example, will a student get into an institute or not, depending on their rank or their marks? That is an example of a logistic regression where we can use it. Okay, then we have what is known as the nearest neighbor algorithm. In the nearest neighbor algorithm, all of these points, the initial yellow and red points, are fed as training data to our model. As soon as we have two new points, what this model does is it will simply see which point is it closest to. Okay, this point is closest to a yellow point, so this must belong to the yellow cluster. This belongs to the red cluster because it is closest to a red point. A very simplistic model, and generally tends to work, but again, not in all situations. All right. Then we have what is known as a decision tree, which will take into account the properties of an object. It will compare the properties of the object and then take a certain series of decisions and then try to classify the object. So here we have a star. It will try to figure out, okay, check for property number 1, yes or no, it goes down one path. Then the second property, it will go down another path, another property, and it will go down and find it as, okay, this is a star. And this is how a decision tree works. But a decision tree tends to become very, very overfitted to the data that we have. And one way to fix this problem or this shortcoming of a decision tree is to simply have multiple decision trees which will decide or classify objects based on different sets of properties. And ultimately, what we have a collection of trees or a forest. So the next classification model is called a random forest, where we have multiple classification trees and they are all evaluating this object based on different properties, not the same attributes of the property, but different properties. And then they will give their individual opinion on what this object is. And then the overall model will take a vote, and whichever reply is the most common reply, that majority wins and that is selected as the result. The principle here is that different decision trees working together in a vote based system will usually have less errors and are much less prone to overfitting. So, this was the random forest method. Then we have the neural network, which simulates actual neurons in our brains. So, what happens in a neural network is that you have some input which is goes to your input nodes, and here they are represented in the red. Each of these nodes will perform some calculation based on their inputs and pass on their outputs to the next to the next layer of nodes. Then they will perform some calculation and pass on the result, and so on and so forth until you reach the output nodes, which will then give you your output. So this is very similar to also how neurons work in biology, and it is another form of unsupervised learning. And all the neural network really does is just keep balancing the weights of how much to consider the outputs from various neurons and ultimately come up with some usually very non-linear and very complex algorithm which classifies objects for us. Okay, all right. Now we come to the final kind of model, which is clustering. And the most popular method of clustering is the k-means clustering. It is a simple and it is a fast method of clustering and is also very popular due to its speed and simplicity. So let us look at what exactly happens in k-means. First of all, we see that we have a lot of data points on our graph right here, which are currently not assigned to any cluster. We are going to start the process of clustering by choosing any three random points as our cluster seeds, which are going to be marked as X. What we have also done is all of these points we have color coded depending on which of these seeds they are closest to. The red points are closest to the red seed, similarly with the blue and the green points. Now, what happens is that the positions of each of these seeds will be updated to lie at the mean position of all of these points. Hence the name K means. So what we are now going to do is we are going to update the position of all of these seeds and then reassign. Okay, now we have reassigned the positions. As you can see, the green seed has moved here. The blue seed has moved slightly into the blue cluster, and the red seed, which was here, is now slightly in the middle. So this process is going to repeat itself quite a few times, right? Every time we shift the positions of the seeds, some of the clusters might just change their cluster membership, because now suddenly you might notice that this seed has moved closer. So in fact, now this belongs to the next cluster. And so eventually these seeds are going to keep moving. As you can see, the seed is slowly encroaching inwards, and some of the blue points are now going into the red cluster. This process is going to keep repeating and all the cluster positions are going to keep shifting. Some of the cluster points here have now started to become blue and are now part of the blue cluster, which will cause the blue seed to move very quickly. And ultimately, we have a final solution where we see that we have three distinct clusters. And at this point, no new point rearrangements are going to happen. So this we can safely say is our final solution. But again, it is sensitive to initialization. So depending on where our initial points were, sometimes it can give us a very incorrect result. Okay, so yes, plus k means can be sensitive to initialization and sometimes can fail us. All right. Also, we have to specify the number of clusters. Now, when we explore our data and we plot it, we see that there are three big groups over here. So we can tell the algorithm that there are three clusters, and then we can decide that, okay, the algorithm will identify that, okay, there are three clusters over here. In the next method we are going to see, we do not need to specify the number of clusters. So let's look at what that is all about. Now, this is called the mean shift. And what is happening here is that again, we have a cluster seed which has a small radius around it. What it does is count the number of points and note the positions of the points in that little radius around itself. And it will keep trying to move wherever there are the most number of points. And it will keep trying to go towards the most dense area available. And so this cluster keeps moving slowly, 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 and will eventually stop. This seed will stop at a point where the density is maximum. And at this point, moving in any direction will only reduce the number of points inside this radius. As you can see, this point count is going up and eventually settles at 152 and 151. It has settled. All right. Okay. Now let us look at this in action. As you can see, a lot of these points are converging into simple cluster seeds. Okay. When it begins, usually these points are going to be spread out all over. Now these points are going to start moving, and as you can see, they are converging in positions. So every time you see 2 points converge to the same position, these two are removed because they are duplicates. What we will be left with is as many cluster seeds as we have points. Finally, we will assign the points based on the proximity towards the seeds. And finally, we get our final cluster. We're going to see that in a moment as soon as this animation finishes playing. And there we have the final cluster. Okay, in this method, each of these points has a small circle around it, right? Any other points which fall within these small circles will quickly be absorbed into the cluster, the main cluster group over here. And so it identifies an entire area. Then it starts with a new area and it will immediately grab all the points within it. And then so we see different areas. This is called a density based spatial clustering of applications with noise. And what happens here basically is that it will start with one point and it will grab all the points within it. So the cluster sort of starts to bleed around the dense regions. As soon as one region is over, it starts with the next region. The points which are still white are just outside of that radius and are therefore marked as noise. Okay, so what about the points that remain white? Basically, they're too far away from the dense regions of this clustering method. So they are ignored and not assigned to a cluster and are treated as outliers or simply as noise. Okay. So in this smiley face, we see ultimately we have a nice little clustering going on, and we have just some white points which will just be considered as noise. Now, there are some parameters to this which we have to specify. One is the size of this circle. Now, if the circles were themselves just slightly bigger, maybe this point would have not been a noise point and would have been incorporated into the blue cluster. Same with this point and this point and this point. And once these points get absorbed, maybe this point would also have been absorbed and this point would have been absorbed. So again, it is sensitive to the window size or the radius of the circles of the points which we have. Second, if we look at the minimum number of points for a cluster, right now in this particular example, it is 4. But if we had suppose 3, then these 3 points here would have been a cluster of their own and not just been marked as noise. So this was the DB scan method of clustering. All right. So continuing on, now we have the Gaussian mixture models or expectation maximization clustering. Unlike k-means, it is similar in its procedure, but unlike k-means, what it does is it also takes into the account the fact that our variables usually tend to be normally distributed. So rather than rigidly saying that this point belongs to this cluster and that's it, end of story, it gives you a probability that this point has so much of probability of belonging to this particular cluster. Another difference from k-means is that instead of just looking at the distance, it allows the distance along different axes to be different. So instead of having rigid circles like the circle with the previous clustering mechanisms, here we see that instead we have ellipses or ovals, right? And also we have two regions for the ovals. One is the inner yellow region, dark yellow region, which says basically there's 99% probability that our point belongs to this cluster. Then the light yellow region is basically 95% probability of belonging to this cluster. And the points outside belong to this cluster, but with a probability of less than 95%. So Gaussian mixture models tend to yield a better result, but also tend to have a slower processing time and are slightly more complicated. But again, they are sensitive to window size if the point density, if the points have varying density. And just like k-means, this requires data exploration so that we can visually see how many clusters we would require. Okay, all right. So this basically gives us probabilities instead of rigid cluster membership assignments and allows for ellipses instead of circles. Okay, now we have regressed our data, we have clustered it, we have classified it. Usually in projects, when we are working on any kind of project, be it marketing, be it some field of research or whatever, usually we will use a combination of these methods. Yeah, these are not standalone methods, and each situation sometimes requires different kinds of models to be used. So it is not sometimes intuitive as to which model we should use for our particular problem, right? But we can generally get a good idea using different kinds of models. Now, how exactly which model to use, that is something a professional would be able to advise you with it, right? But once we have modeled our data, we have to now look at whether our model is accurate and has indeed captured the underlying logic. Okay, but that is not going to be explained to you by me. That is going to be explained to you by Samir. So for now, that is all from me. And I'm going to hand it back now to Samir, who will take you through the next and final stage of data wrangling, which is testing your data. So Samir, take it away.
Thanks, Prateek. But before we actually do that, let me actually take some time and have you guys take our second survey, which is just essentially asking, based off of what you've seen for data modeling, uh, does your organization make use of the advanced analytical and predictive modeling examples that we had shown you during this webinar just now? So feel free to take some time and key in your answers. And once you have done that, just a few more seconds, I see some people still answering. Okay, great. Thank you so much. So let's let's move on to model testing. So I think the first question that you might want to ask is, so what does data testing consist of? Well, at its core, testing consists of a couple of major points. First, you want to be able to do confirmation testing, where you can take two models and run the data through both, and by testing them, you can confirm that they're getting the same answer. So in the example we have here, we took a logistic regression model and a random forest regression model, and essentially ran the data through both to see if we got the same, we got results that are matching. The other way that we can consider is using p-values to identify which variables in our model are not contributing or affecting our overall clustering or results. Oftentimes, you can think of it as the example of when working in a group project, you might have one or two people who is, for lack of a better term, asleep at the wheel. But the project still succeeds, and so unless you actually kind of went in and did some focus, you would not have caught the people kind of slacking off. The third option is you want to be able to, the third step is determining whether your model is suffering from not capturing the underlying logic of the data. For example, if your model has overfitted or underfitted your data. So let's dive into those three concepts. Let's start with confirmation testing. So the idea behind confirmation testing is taking a model that you did not previously use uh, to model your data and run your data through that model to see if you are going to come to wildly different results. The idea is that, take for example, we have the data points for these four graphs are from the same data set. However, you'll see that each of these models is approaching the uh, plan of dividing these into two separate clusters in a different way. Whether that's the decision tree, the random forest, the neural network, or the SVM. And so you'll see that the idea behind using confirmation testing is that suppose that the first test that we had used was the neural network or the SVM. You'll see that we have some values that are supposed to be marked as members of the blue cluster who were marked as in the same section as the red cluster. So these grouped values might be singular points, but being able to identify that this is something that might be happening and that these might be misfiled values can be resolved by also running your data through a decision tree or random forest, where you can see that you have a difference in whether how the model classifies certain points. Being able to identify this might make the difference when it comes to the decision that you come to about your data as a whole, which is part of the reason why this is so important. Let's move on to the second consideration of data modeling, which is p-value evaluation. So the idea of p-value evaluation is that by taking all of your observed data, you can essentially sketch the relationship between your dependent variable y and each of the independent variables x1, x2, and so far, and so on until xn. The idea is you want to calculate to find out whether the relationship that you find between y and each of these x values is a coincidental relationship or a relationship that is indicative of actual correlation. So let's look at the example we have here of an OLS regression. You'll see that the significant variables have a p-value of 0, whereas the other values have non-zero p-values. This means that, for example, we can see that our constant has a p-value of 0, which means that it's clearly having a major value of significance to how the y value is generated. And similarly, x2 also has a p-value of 0. Compare this to x1, which has a p-value of 0.781, which means if we're looking critically to see if there's a correlation, there is a 78% chance that the correlation that we're finding between these two variables is absolutely coincidental. This is important because it lets you identify which variables might not be useful for answering the questions or trying to find insights from this particular data set. And that can be used to inform future decisions when it comes to data modeling and data collection. The third section of the data testing sequence is considering overfitting and underfitting for our model. So what do we mean by that? Well, the idea is if a model is overfitted, the curve or the underlying logic that is used will fit perfectly to this data, but it will miss the underlying logic. Suppose that we have this new point that gets added to our model. While the previously existent points were a perfect fit for our model, this new point is clearly an outlier now. And this is the error that we might encounter. We have no variance between any of our given data points and the line of best fit, but conversely, new data that might get added or new observations will throw our model off. The opposite problem is underfitting, where essentially the model is not even really making a large effort to capture the logic of the data. For example, this line does not even account for the fact that we can clearly see there is a slight exponential curve to how our data is related on the x to y axis. Therefore, it doesn't make sense to use this linear line. Compare this to the correct fit for this data. The correct fit here is an exponential curve because while yes, it does not intersect perfectly with all of our points, each new point that we add should probably fall such that it is within a reasonable variance of our line of best fit. Being able to identify whether you have overfitted or underfitted a curve is important. And there are a couple of methods we can utilize to correct. For example, we can correct overfitting by splitting our input data into a training set and a testing set. First, we can train our model using the training data set to come up with an idea of the correct curve or line of best fit. Then test with the testing data to confirm that the line we've drawn is accurate. Similarly, to resolve the underfitting problem, we can use different modeling methods which can capture the modeling data. This goes back to the idea that we had of confirmation modeling. If we believe that our model is underfitted and we test the model and find wildly different results, we can tell that we were underfitting in our prior model choice, and that needs to be taken into consideration and might modify what we are going to do. So let's move on to the third webinar question, which is on these 3 points of data modeling, which is how confident are you in your company's analytical model testing strategy? Please take some time and okay, I see that everyone has answered this poll actually very quickly. So let me give this a close and let's move on to the next point. So to quickly summarize, data modeling is the key linchpin in the data wrangling process as it converts the data into a format for insights to be drawn. There are numerous types of data models, each with their own unique function. Classifiers classify and sort your observations. Regressors find relationships between the variables that you're using. And clustering groups our data according to similarities or dissimilarities so that we can determine whether groups have certain qualities that are in common. Data model testing allows us to test and confirm the insights we make with our data model so that our insights are factual and actionable. So this settles the 2 points we've covered here, but let's cover the data wrangling process as a whole. Data wrangling is essential to enabling the utilization of an organization's data assets. Data sampling will help us focus on the segment we want to study and reduces the data size that we're using and handling in order to find those insights. Data exploration helps us spot the general patterns and trends as well as pitfalls that we might need to avoid. Data cleaning standardizes the format of the data and removes inconsistencies and errors to improve the quality of the data. Data modeling captures the logic of real-life principles and uses them to help accurately predict in uncertain scenarios. And finally, data testing will help us inspect our model to ensure that it is accurate and helps us make the tweaks to improve our model so that our data wrangling is of value. That brings us to the end of our webinar and our webinar series. Thank you so much for taking the time to view our webinar. We know that we've actually gotten quite over time, so thank you for sticking with us. And if you have any additional questions about what Express Analytics might be able to do for your organization, or even any questions related to the content covered in this webinar, please feel free to contact us at any of the lines of communication listed here. Other than that, thank you so much for your time, and we hope to see you again at our next webinar series.
Thank you, everyone. Thank you for joining. Have a nice evening. Have a nice day. Yeah. Bye.
Goodbye.